here of integration, and it's similar to one we've already done, so it's a little bit of a change, but it's very similar. So we're talking about the area between two curves now. We've looked at the integral as representing the area between the curve and the x-axis, and when we find that area, we've been saying that integral is assigned to value, meaning if it's below the x-axis, it's negative. If it's above the x-axis, it's positive. This concept we're going to do today, it's called area between two curves. Now, we're not going to integrate down to the x-axis, just between two curves. And we're talking about the area between the two curves. I got to cancel this iTunes thing. All right. So the area between the two curves is, oh God, get rid of that. Sorry. Is always going to be positive because we're doing subtraction here. You're going to see what happens, but I just want you to know that this is different than what we've been doing in terms of signed area. Like area that shows up below the axis when we do this, it's not going to be negative. We're doing the area between one curve and another. It's going to be always positive because we're actually talking about area of a region. It doesn't matter where it is on the graph. So we're going to start with this first one here. We're going to build up towards that. And a lot of today's video is going to be really based on calculator work because a lot of these are calculator questions and how you can work your calculator to do the problems more quickly because, as we know, saving time on the test is key. All right, so first they ask us to graph the function and find the value from -5 to 0 of the integral of f. And this is a review of what we've been doing. So we are going to do this first page or page and a half without our calculator just to get the idea down. So I want to graph this parabola. It opens downwards, so I need to find the vertex, which is the maximum. Now I could do -b over 2a, but since this is a calculus class, we're going to review a concept here, and we're going to take the derivative of f, which will be -x, and then -2. We're going to set the derivative equal to 0 because that will find any maximums or minimums. So I get x equals -2. So I get that I will have a maximum at x equals -2 or a minimum. I know it's a maximum. I don't have to do the sign analysis here because I know that the parabola opens downward. But if I wanted to, I could go f prime, put my -2 on there, and test my derivative. If I plug in -3, I get 3 minus 2, I get a positive for the derivative. And if I test 0, I get a negative. So the derivative switches from positive to negative. That makes it a maximum. To find the y value, I'm going to do f of -2. So if I plug in -2 there, I get 4 times -1/2 plus 4 plus 4. That's going to be 6. So the vertex, I know, is -2, 6. Just a little review of some derivative calculus there. So -2, 6 is our vertex. We need 3 points to graph this parabola. The next easiest point would be to find the y-intercept. I plug in 0 for x, I get 4 for y. Then, because of the line of symmetry that goes down the center of the parabola, I know there'll be a symmetric point over there. So there is our 3 points, or there are our 3 points. So now we can graph our parabola. It looks something like that. And then they want us to use a color to shade underneath that, so I'll stay with this green color. And when we find this integral, it's going to find the area from -5 to 0. Oh, I picked up the pencil. This looks sloppy. I'm going to do that again. So we're going from -5, oh boy, to 0. So that integral is going to represent that area there. Right, from -5 to 0. So that's a graphical representation of the integral. Now we're going to actually calculate it. We've been doing a lot of calculating integrals with graphs. On this one, we have our equation, so here's a good chance to practice our fundamental theorem of calculus, part 1. So first we've got to find capital F of x, which is the antiderivative. So it's x to the third times 1/3, so it's -1/6 x squared. Divided by 2, it's going to be -1 plus 4x. and we're going to evaluate that from -5 to 0. So here's where you're going to plug in capital F of 0 minus capital F of -5. Don't forget to distribute this negative sign when you start working on the capital F of -5. I'm going to say pause the video here, work this out, and see if you can get the answer I get. And don't just wait for me. Do it yourself. You need to practice this. Okay, welcome back. So I got 145 over 6, and we'll just call it square units because it's an area and they didn't tell us what the units are. Okay, now it says graph a new function, g of x equals 1/2 x plus 4, so that's a line. We'll do it in a different color. We'll go with pink here. So the y-intercept is 4. The slope is 1/2, so I would go down 1, left 2, down 1, left 2, down 1, left 2, down 1, left 2. Okay, so we graphed it there. On the same grid above, then find the value using a different color. So we'll use a pink shading here. So that when we calculate the integral under the line to the x-axis, it's going to represent that pink area. Okay, so I'll stay with this. So now we're going from -5 to 0 of 1/2 x plus 4 dx. So again, this is a good chance to practice our anti-differentiation. This is power rule, so it's x squared, it's 1/4 plus 4x. So we evaluate that from -5 to 0, so that's going to be capital F of 0 minus capital F of -5. You pause the video, take a second to calculate those numbers. Again, make sure you're doing this. Okay, welcome back. I'm getting 55 over 4 square units. That's the pink area. So now what we're going to talk about today is really the area between the two curves. So I'll do this in white here. What do you suppose you would do to find the area of the region that is located in between those two graphs? So I want to find this white area here. I shaded that in white. How do you think I find that? Well, I take the green area, I subtract the pink area, and I will have the area in between. So subtract the two areas. So the area in between will be 145 over 6 minus 55 over 4 equals 10.417, or 125 over 12. I'll leave it as 10.417. This is why this area is always going to come out positive, because we're always going to subtract the bigger area minus the smaller area. So that's why we always get a positive area. Since we're talking about area, we're just going to make it positive all the time by always subtracting the bigger minus the smaller. And we'll talk about how we do that. All right, so that's how you find the areas. Now, is there a faster way to do it than doing each integral separately and then subtracting the answers? Yeah, you can just subtract the functions as long as you do the upper function minus the lower function on that interval. So if I do the top function here is the green function, it lies above the pink function. So that's why we're doing f of x minus g of x. If we do that, it'll come out positive, and that's kind of what we want, because when we start talking about the area, look, I can make it be negative if I do g of x minus f of x, because some of you are going to ask, why is it always positive even if it's below the axis? Because we're talking area. In this unit, we are no longer talking about signed area, just area. So we're doing the absolute value. It's always going to be the upper function minus the lower function. So we're always going to get a nice positive area here. The signed area is for when we're doing the area to the x-axis. But if we're doing the area between two functions, it's always going to be positive. And we're going to talk about it as such. All right, so let's do this integral numerically, or I should say with the functions, not with the graph, and see if we get the right answer. So if we do the top function, so f of x was the parabola is above the line. So if we do, what was the parabola's equation? -1/2 x squared. So minus 2x plus 4 minus the line, which is 1/2 x minus 4. It's minus 4 because it's really minus 1/2 x plus 4. We got to distribute that negative sign. Dx. Technically, I should put this all in one big thing to show that that's the integrand. That's the thing that we're integrating. I can simplify before I go ahead and do the power rule. I got negative 1/2 x squared, and then I can combine these x's. So negative 2 minus 1/2 is negative 5/2 x. And then the 4 minus the 4 is 0, so it's just this. Now I can apply my power rule, so capital F of x is going to be equal to x to the third, and it's going to be negative 1/6, and then it's going to be x squared minus 5/4. And we're going to evaluate that from negative 5 to 0, so you're doing f of 0 minus f of negative 5. We know it's going to come out positive. Pause the video here and evaluate. Okay, welcome back. We get 10.417. So this just shows what we knew graphically. So we don't need to do two separate integrals. And plus, we already knew a property of integrals, by the way, that if we had the integral of f of x minus g of x, that's the same thing as the integral of f of x minus the integral of g of x. I should have dx's on these, sorry. Right? So in this case, now we're just kind of saying if we go backwards, that's also equal, because up here we did the integral of f, then we did the integral of g, and then we subtracted the answers. That's this piece here. If we go backwards on the property, yeah, we could do it just like this, of course. All right, so what do you notice about this value? It's equal to the value, it's the area between the two curves, and it's equal to the value that we found that represented that. This brings about the general way that we find the area between two curves. So we're going to always integrate over the interval, and we're going to always do the upper curve minus the lower curve. So what we're going to say is to find the area between curves, and it's not the signed area. It's just the area, meaning it will be positive. That's going to be the integral from a to b of f of x minus g of x dx. Really should kind of make that the integrand there. Provided that f of x is bigger than g of x over the entire interval. So that's just saying we always do the upper function minus the lower function, so our area comes out to be positive. All right, so let's do an example here. So we've got the integral from 0 to, it looks like they intersect again at 2, right? We're going from 0 to 2 here on the x-axis. When we make our intervals, we're integrating across the x-axis, so it goes from 0 to 2. That's how I think about it. The upper function here, they don't tell us which one's the upper, but I know that the sine curve starts at 0, 0 and starts by going up first, and that's what this is. It might have a different period or whatever, but it's going up first. So even though the bottom one looks like a parabola, it's really a cubic. We're just looking at a section of it. So the upper function is sine of pi x, minus the lower, which is x cubed minus 4x. And that's our integrand dx. So first of all, what we're going to do here, I think, is we're going to break this into two integrals. Sine of pi x dx, so we can integrate one at a time, plus the integral of from 0 to 2 of negative x cubed minus 4x dx. All right, so this guy looks like a composite function where my inner function is pi x. So what's the derivative of pi times x? It's pi. So this would work. I could recognize this as reverse chain rule if it had a pi there, right? So I just want to have that derivative out front. So I'm going to do that. I'm allowed to, pi is just the constant, so I'm allowed to stick a pi in there. Sine of pi x dx. I can do that if I also multiply by 1 over pi on the outside to keep my coefficient 1. Plus, from 0 to 2, I'm just going to, actually I'll integrate this one to show you that I can integrate kind of one part at a time, and I can write it, you know, I didn't integrate the first part, but I can integrate the second part. So I've got x to the 4th minus, so that's a negative 1/4, and then x squared, so that's a minus 2. And that one's already integrated, and we want to evaluate it from 0 to 2. I just kind of write it like that. Even though I haven't evaluated it yet, I'm just going to write the 0 to 2 part to say that I need to. And that's for this thing. All right. So actually, that's why we use the backwards things, right? So I can go from 0 to 2. I got to evaluate that part. Over here, the 1 over pi comes along for the ride. This I recognize as a reverse chain rule. So I got to do the integral of the outer function. The integral of the outer function is going to be negative cosine. I'm going to fire the negative in front of the 1 over pi. And instead of x, I got to keep my inner function. All right? So then it's plus a negative, so I'll just say it's minus 1/4 x to the 4th minus 2x squared. Now the whole thing's been integrated, so I can evaluate it from 0 to 2. I'll do it like this. Okay, so pause the video, take a second, and evaluate that. Welcome back. I hope you're not cheating this. You really need the practice of doing capital F of 2 minus capital F of 0. This stuff shows up on the test. It's not as easy as it looks. You got to do it. You got to make sure you get the right values. Please. These are the things we don't want you to get a question wrong on an FRQ, lose 2 points or 1 point for not evaluating correctly. These are easy points you got to get, but you got to practice them. Okay? So don't skip out on these. You should have gotten 4. So 4 would be this area here, the shaded region R. And it would be units squared. All right, this one we're going to finally move over to our calculator from this point forward so we can practice doing some stuff with the calculator. All right, so pictured to the right is f of x, blah, 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 and a different line L, which they don't give us the equation to. They just say it's tangent at the point 0,3. Find the area of region R. So the line has nothing to do with that. So first of all, we're going to start by going to y equals, and we're going to put that function in. So I'm going to go alpha. I'm going to use that numerator denominator thing. So we've got x cubed over, I'm not going to make you watch me do this. Can you pause? Oh, wait, I can't pause the video here. I should have put this in before. Let me see if I can pause the video. Yeah, no, I can't. Okay, so you got to watch me do this. Over 4, I'll try to go fast. You should be doing this as well. Minus, we'll do alpha. I'm not going fast at all. X squared over 3. I'm just talking because I'm bored, I guess. So I got x to the third over 4 minus x squared over 3 minus x over 2 plus 3 cosine of x. Let me make sure I'm in the proper mode here. We want to be in radians, which we are. So there's our y1. Okay, so we've got that in there. Now, if we're going to integrate, we have to start at this point here where it crosses the x-axis, and we're going to 0. So I'm going to call that x value a. So we're gonna define what a is. We're gonna tell the reader what a equals when we find it, but then we're gonna have our calculator store it. So we're gonna go from 0. Oh, sorry. We're gonna go from a to 0, the integral of y1 dx. If I do that in my calculator, if I call this part y1, that equation, right? That's gonna give us the region R. So that's the area of region R. Again, why? Where do I get this stuff from? A to 0, so I'm integrating from A over to 0, and the only curve involved is this curve here, y1. It's the area underneath that to the x-axis. So it's not between two curves. I don't need to do like upper minus lower since it's going to the x-axis. If I integrate that, I'll get my answer. So let's do some calculator work here. So I want to find out where it crosses the axis. So the easiest way to do that is to do the intersection piece. Oh, so here's a good lesson. Look how long it's taken to graph this thing when I do a full window. I'm going to pause it, and I'm going to go back to my window. I really only want to look from like -2 to 1. So my x min will be -2. My x max will be 1. And the y's only go up to 3, so I'll go y min. Whoops. I'll go like -1 up to 4, let's say. Hopefully that graph's a little faster now. Let's take a look. Nope. I guess a little bit. Started a little faster. So we're looking for that point where it crosses the x-axis, and we want to call that A in our calculator. So here's where the calculator skills come in. So first of all, let me find the point of intersection. So that point of intersection, I'm going to do second, calculate, intersect, and that's easier than finding zeros. That's why I put the line y equals 0 in. First curve is blue. Second curve, yeah, I'm on the red curve. I hit enter, and then they want to guess. I'll move my cursor somewhere in the ballpark just to be safe. Hit enter, and now it tells me, it's still working, it tells me my point of intersection is there. So I'm going to let them know what it is. A is -1.373122. I'll give them the full number. Why not? All right, now when I quit out of here, remember that number is stored as x. So I'm going to call x. Whenever you find an intersection, it stores the x coordinate as x and the y coordinate as y. I'll call x, there's that number, and I'm going to store it as A. So now I can recall it whenever I want as A, so I don't have to type it in. All right, so there's my A. I have it stored. So now on this screen, I want to integrate. And you want to store it as A because you never know, you might have to use it again later in these FRQs, and you usually do, these points of intersection. You want to store them. All right, so we want to calculate this thing, so we're going to go alpha F2, we're going to do F int, so we can go from A to 0 of y1 dx. All right, and we should get, yep, that's the correct answer. We always want to go to 3 decimal places. 2.903 is what we get. And that's the area of region R. Okay? Now, find the equation of line L if it's tangent to the graph of f at 0, 3. So, to find the equation of that line, the point of tangency, they already tell us, is 0, 3. The slope of the tangent line, we need to find the derivative and then plug in 0. So, since we're using our calculator, we're going to go alpha F2, I think it is, yep, and derive. We're going to find the derivative with respect to x of function y1 when x equals 0. So the slope of that tangent line is negative 0.5. That's going to be round off error. When you see that many 9s, we're going to call it negative 0.5, which is -1/2. Okay? Yeah, so we're going to call it -1/2. So let's write our equation. It's me y minus 3 equals -1/2 x minus 0. So there's the equation of the tangent line. Is that all they asked for? Yes. Alrighty. At what ordered pair other than 0, 3 does the graph of line L intersect the graph of f of x? So now I want to find this other spot right here where they intersect. Okay, and I can refer to that. Well, we'll get there in a second. So we want to find that point of intersection right there. That's the only other spot they intersect. So what I need to do is go to y equals, and this time I'll make y2 equal to the equation I just found. Now I got to solve it for y so I can plug it in. So I get negative 1/2 x plus 3. I'm going to pause it because I need to see more of the window now. I forgot about that. So now I want to see, still don't have to go higher than 3, but I want to see over to 4, let's say. So I'm going to get my x coordinate to go over to 4 and take a look at this thing. Here's where you get your break on the test. Enjoy it. You get like a 30-second break to just watch this thing graph and zone out. All right, we want that point of intersection right there. So we're going to go second, calculate, intersect, number 5. Yeah, blue curve is our first curve, red curve is our second curve. We got to get closer to this point of intersection than the other one so it finds it. All right, there we go. It's thinking, it's working, and there it is. So I'm going to call that x value here, just the x coordinate, I'll call that b because we're going to use it when we integrate probably. So, yeah, so we're going to tell them where it intersects because that's what they want. So it was at, and I'm not even going to round, I'm going to give them the full decimal, 3.389, I can't see, 8677, my eyesight's getting bad. Oh boy, 1.3050662. Now remember, when you calculate that in the on the graph screen, it's now saved that as my new x value. So I want to store that as b. So I'm going to call back x by just hitting x and enter. So there's that new x value. And I'm going to store it as b. All right, so now I have that as b. And I'm going to let them know that as well. I'm going to say b equals 3.3898677. We'll round at the very end. We don't want to round before that. Okay, you don't want to do that with these limits. Keep them the full number. Okay, so that's just some extra information. This was the answer to the question. Find the area of region S. So the area of region S would be if we integrate from 0 until what x value? That b, right? So we're going to integrate from 0 to b. And now we're not going down to the x-axis. We're integrating from the line is the upper function and the curve is the lower function. So the upper function is the line which we called y2 minus our other function which is y1 dx. All right, so we want to go and calculate that. So alpha f integrate, and we're going from 0 to b. So we don't have to type out that crazy decimal, of y2 dx. Oh, what am I doing? We got to subtract y1, sorry. Minus y1, as if you can't see what I'm typing. We should get 6.9, yep, there it is. So 6.98, here's where we can round to. That's the area of region S, because we did the area between two curves. We did upper curve minus lower curve, and the limits go from where they intersect, from 0 to whatever the x coordinate at that point was. So there's a lot of calculator skill going on here. We're going to do one more. Yeah, good. This one's got a lot of calculator skill on it as well. All right, so picture the right R and S, which are formed by the graphs. I'm going to make them two different colors so I can keep them straight. This graph, the green one, is the sine one, right? So that's going to be our y1, the green one. I'll put a y1 next to it. And then our pink one is going to be that exponential function. And we're going to call that y2. Okay, so we're going to go back to y equals. We're going to change those out. y1, y2. All right, so y1, I'm not going to use the fancy fraction here because I really don't need to for 1/4. It's only when my fractions are a little more complicated. I didn't really need to on the last one either, but I just wanted to show you where that button is again. Sine of pi x. Pi is a second, I think, right? Where is it? Where the heck are you? Pi x. All right, so that's our y1. y2 is 4 to the negative x. Oh, I put 2 x's in there. Yikes. Delete. Okay, so they're in there. What are they asking for? Identify the points of intersections of f and g. And when I start integrating, those points of intersection are always important. So I'm going to remember the x values because I'm going to use them when I integrate. So for this point, I'm going to call that point of intersection A. And for this point of intersection, I'm going to call that x value B. I'm going to remember those. All right, so they want those points of intersection. So let's see, what's our window here? We don't really know, right? So I'm going to go zoom standard because I'm not sure what this graph looks like. Okay, so that was way too big of a window. All right, so they intersect there. I'm going to zoom in. I like zoom box actually in this kind of a situation. So I move the cursor to the upper like corner. I don't know, like that. And then I make a box around what I want to look at, just below the x-axis, and then over just past where they intersect. And the blue one goes back below. That's the part we want to look at. All right, so there we go. This is a good look at what we want to see. So that's zoom box. All right, let's find those points of intersection. So second, calculate intersect. We got our blue curve. We got our red curve. Let's move close to the point of intersection we want to find. There it is. We hit enter. Let it tell us. So the first point of intersection is 0.178218, 0.7810917. When you're reporting the answer, you could round them if you like. Before I go find the other point of intersection, I'm going to quit out of here. I'm going to call x because I want to save that x value for a limit of integration. I'm going to call it and I'm going to store it as a. And I'm going to write it over here on my graph so I know. I'm going to let myself know that x value is a and that x value is b. Okay. So where was I? So that's a. Now if we go back to our graph, we want to find the other intersection. So we're on the blue curve, so we hit enter. We're on the red curve, we hit enter. And then they want our guess. So we got to get over near that other one. This is why the color calculator is helpful. So that point of intersection is at 1, 0.25. So I don't need to store that as B because that just occurs at 1, and I might even put it on there 1 and then 1/4. So that's nice. I don't have to store that one. We're going to let the reader know that we called A 0.178218 before we start integrating. You got to kind of let them know that, okay? All right, so find the area of region R. So the area of region R, we're going to integrate starting at 0, because that's where this left bound of the region is. To the right bound is at A, so we're going to stop at A. And the upper function is y2, and the lower function is y1. And that'll calculate the area of that region. So we're going to put that in our calculator. So we're going to do f int. And we're going from 0 to a, y2 minus y1. And I got, last time I did 2.903. So something's wrong there. Is our A not stored correctly? A was the 0.17. Our Y2 was the pink, and it's on top, so it should be Y2 minus Y1. I'm a little nervous that A is not stored properly. No, it says it is, but I can check. I can call A. Okay, it's correct. So I integrated from 0 to A. We're finding the region R. Oh yeah, it's 2.9. Yeah, it should be 2.903 is what I got. Oh, I'm on the wrong thing. I'm sorry. I'm looking at the wrong thing. I'm on the last problem. I'm checking my answers to the last problem. So 0.065 should be our answer, and it was. All right, so yeah, we rounded at the end to 3 decimals. 0.065. Sorry, I still had the answers out from the last problem. I was going to say, that looked good to me. They're set up. All right, find the area of region S. So now S goes from A. We're going to integrate from A to 1. And this time the upper function is y1, so it's going to be y1 minus y2. So we're going to go from A to 1 of y1 minus y2, because this time y1 is the upper function. All right, so let's go up here so I don't have to go to f int. Here's your copy feature, right? You go highlight it, you hit enter, and now we can edit. So we're going this time from A to 1. So alpha A to 1. And now we're doing y1 minus y2. .410. Good. 0.410. That's the area of region S. Find the area of the unshaded region bounded by the graphs of F, G, and the x-axis. So they're looking for this green area in here. And the way I would find it is, let's see, if I find, I'll shade it in this like light blue. If I find the area under the curve y1 to the x-axis, which we haven't done yet, but if I find this blue area, which is simply the integral from 0 to wherever this crosses the x-axis, I don't know where that is yet, I got to find that, but if I integrate that, I'll get the blue area. To get the green area, I can subtract out this white area, S. If I do blue minus white, I'll get green. That gets a little confusing looking, but that's how I'm going to do it. The blue minus the white will give me the green. And I already found the white. The white area is region S, right? So I just got to subtract that out. So first, I've got to find that blue area. And what I need to do is find the intersection. I need that point right there where it crosses the y-axis. I'm going to go to y equals. I'm going to put in a 0 so it's easier to find it for y3. I don't really care at all about the pink curve, right? So I don't even want to graph that pink curve. So I'm going to turn it off to save some time when I graph it. Don't care about the pink curve at all because I'm finding the area under y1 right now. Finding that blue area. So first I need to intersect. So the y3 graphed as a black line, so it's hard to see. But we're going to do second. Calculate intersect. We got the blue curve. We got the black curve. And now we got to get over close to that intersect. There it is. Let's find that value. And I'm going to store that. Well, I don't want to say x. So that's stored as x. So I'm going to quit out. I'm going to call x. And then I'm going to store it as b. And we're going to tell them that b, we want to find what, the white area. So b, I'm going to use a white Okay, maybe not. Having trouble. Technical difficulties. We're going to tell them that B equals 1.080430623. And it's stored as B already. All right. So to find the area of the white, we're going to do the area of that blue. And that's going to be the integral from 0 to B of the green function, which we called y1, minus the region S. And that would be that green area. And we know S is 0.410. But if you want to just go through the integral again, remember we have A saved. So that's going to be A to 1 of y1 minus y2 dx. So if we wanted to just do it all again, we know this part is equal to 0.410. But if you want to give the reader like the full thing of what you're doing, or you just want to practice writing it, it's a good idea. So we're going to store that answer as B. So now we're going to do f int. What's that number? 4. We're going to go from 0 to B. Of y1 dx minus the integral from A to 1 of y1 minus y2 whoops, we'll get that x out of there. Uh-oh. Oh boy. Okay, we're going to decline the Gordy-Koff for now. Delete. Okay. We're going to hit enter. We're almost done here. It's a race against time. So we get 0.486 after we round it. That's what I got before. That's that white area. We are done. That's not where I wanted to stop.